Now, when we are dealing with exponential models, a lot of times we will deal with exponential or logarithmic models when we are referring to growth or decay of population or bacteria, stock market. These are very good examples of where exponential models are going to be utilized. One of the formulas that we are going to be dealing with is the exponential formula, which says Q is actually equal to Q naught times 1 plus R raised to the T power, where Q naught gives me my initial value, stands for the initial value. We have R is my rate, deals with the rate, and T is in terms of times. It can be in terms of years, months, or whatever the problem is actually dealing with. That's what T is going to be in terms of. So again, we are referring to an exponential model. And you can find me in your textbooks on page 572. And I'm going to be looking at number 28 on page 572, number 28. And with this, we are going to determine if it is exponential growth or are we dealing with an exponential decay. So these models can be a growth or it can actually be something that is decaying. So when it grows, that means it's increasing. When it decays, that means it's actually decreasing. And this is what we want to determine as we go through our problems, because it's going to change up the problem just a tad bit from it growing to actually decreasing. Let's look at the requirements for number 28. It talks about exponential growth and decay laws. Consider the following cases of exponential growth and decay. Again, I am on page 572, number 28. Part A, we want to create an exponential function of the form Q is equal to Q naught times 1 plus R raised to the T power, where R is greater than 0 for growth and R is less than 0 for decay. To model the situation described, be sure to clearly identify both variables in your function. Part B, create a table showing the value of the quantity Q for the first 10 units of time, either years, months, or hours of growth or decay. And then C, we want to make a graph of the exponential function. So again, ladies and gentlemen, we are starting out with number 28, and 28 talks about the number of restaurants in a city that had 800 restaurants in 2015, increase at a rate of 3% per year. So when we're talking about increasing, this will be an example of an exponential growth. This is an example of an exponential growth. This is important, and the reason why it's important, because when we actually define what my function Q is actually equal to the initial value that we actually have for number 28, started out with 800 restaurants. So therefore, we will have 800 times 1 plus my rate, we say, is 3%. So converted to a decimal, 0.03 raised to the T power, or just simply saying 800 times 1.03 all raised to the T power. So this here is what my Q is going to be. Again, we are looking at the information from number 28. And this is part A. So what I am going to do, I'm going to use Excel to actually define my table. So come up with the values of Q, which is equivalent to saying X, the Y values. And then we're going to graph the points in Excel. So I will stop sharing. Please remember the function that we are referring to. And the function, as I first stated, is 800 times 1.03 all raised to the T power. That's the function that I'm going to be dealing with. So going to Excel, and you can use Excel, I think will be something that is very convenient that pretty much everyone has. If you're dealing with a MacBook, you have some equivalency of Excel. And what I have already done is set up my first variable, which is time, because they want us to actually have the first 10 units. And I'm going to start at 0 and go up to 10. Now, if you recall the model, and I'm just going to put it in this cell here, 800 times 1.03 all raised to the T power. That is the function I'm going to actually put in to find out what the regular Q is, or the exponential model value. So this is how we're going to do it. We're going to say equal 800 times, open parenthesis, 1.03, close parenthesis, caret. Now we want T to start out at 0. So instead of putting the 0 there, I'm just going to put the cell that contains 0, because once we do it once, and we're just going to copy it and drag it down for the others. So you will see me click on the cell that has 0, and in my case, A4 contains the value of 0, and you will see A4 there. If you hit enter, this here is the value, which is 800. Now, what I'm going to do next is actually click back on that cell, and you should see a little square at the bottom right. We're going to put my mouse on it until the mouse becomes like a thin plus sign. Click, hold down the right button on your mouse and just drag it down, and you will get the other values. So that's why using Excel is very, very straightforward and to the point. Is not bad, and is not tedious at all. Any questions so far? Any questions? Any questions? Now, the last part is, and this is the table that part B is asking us for. So all you have to do, if it was pencil and paper, just copy down these values that you have from this table. And the last thing, part C, is to graph these points. So what I'm going to do, I'm going to highlight this whole table. So you will see me, and including the column labels, I'm going to highlight it and drag it. So I got the first 2 columns actually highlighted. And I'm going to go to Insert. At the very top, you're going to go to Insert, and you will see charts. And you may not see what you need. So there could be that little arrow down at the bottom to see all charts. If you click there, what we're going to do is go to all charts, and we're looking for the scattered, the X, Y scattered. And we're going to click there. And once you click there, you want it to be plotted just the actual values, X, Y value. So you will see this is not the chart that we want. We want this second model. So we're going to click second model and hit OK. And here is the graph for letter C. Last part, I would like to have the lines connected. So if you notice, there is still another plus sign. Hit this plus sign, and you will see at the very bottom where it says trend line. click that box and you will see your lines actually connected. And that's your graph. This is letter C. Any questions? Any questions? And again, if this was something that you had to submit electronically, you can actually save this Excel spreadsheet and upload it for your answers. Clean cut and to the point. You can do this on a calculator. If you were just using pencil and paper, that will be fine also. So either way you look at it, what we are trying to do here is actually, number one, create our exponential function. And again, this is an example of a growth function. Once we do that, we want to create a table of the first technically 11 values, because we're starting at 0 and going up to 10. And then last but not least, graph the points and connect the dots. And that's it. Any questions? Any questions? All right. If not, we are going to do one that is exponential decay. Remember, this one is actually growing. So now what I'm going to do is look at one that is actually decaying. So let's look at number 29 in your textbooks, number 29. So with number 29, it says a private-owned forest that had 1 million acres of old growth is being cleared cut at a rate of 7% per year. So again, this here is an example of a decay. So we're taking away trees in this particular example. So real quick, as I go back to my worksheet, and again, we're starting out with our formula. Q is equal to Q naught times 1 plus R raised to the T power. Now remember, Q naught deals with the initial. Where did we start out at? We started out with 1 million trees within this forest, but it is actually decreasing at a rate of 7%. So instead of saying 1 plus R, which is the rate, we will say 1 minus our rate, which is 0.07 raised to the T power. This is how you will convert it from a growth to a decay. So if you are subtracting your rate off of it, it's decay. If you're adding, it is growth. That's the difference. So we have 1 million times 0.93 raised to the T power. So this is our function that we are going to be dealing with, which is Q. Remember, we're still going to be dealing with T starting at 0 and incrementing by 1 up until 10. But all we have done is just change the function. So at this point, ladies and gentlemen, I'm going to go back to my Excel spreadsheet, and I am going to basically come up with my table, and then I'll graph my points, connect the dots, and that will be B and C. So again, in Excel, and all I'm gonna do is just go below here and start it back up again. So here is my time and the exponential model. Which, if you just want to call it Q, T, and Q, that is fine also. My time, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So all I did was just put those values in. Now, remember, we stated that my new equation was 1 million times 0.093 raised to the T power. So that's the function that we're going to be utilizing for here. So remember, we're going to say equal 1 million, open parenthesis, 0.93, closure parenthesis, caret, and then in this case, it's going to be A22 that I'm going to actually put in there because I want that 0 to be there. Questions? Any questions? Again, if you hit enter, if you hit enter, you should come up with 1 million. And please, ma'am, sir, make sure in between the 1 million and the start of that parenthesis, you have to put a multiplication sign there. If in between there, if you don't, Excel is not going to accept it. So it has to look like this: 1 million, multiplication symbol, open parenthesis, 0.09, oh, excuse me, 0.93, caret, A2. So now we just go drag it down and we have our other values here. Any questions? Any questions? All right. If not, the next part is what we want to do is actually graph this. So again, we're going to highlight the table, these two columns here. I'm going to go to insert, and we're going to go to the scattered diagrams. If you don't see it, again, hit all charts, that little button, go to all charts, go to the scattered, and here is the exponential model that we want. Hit OK. And now you see that the line, the dots are decreasing, going down. And that's what we want because we already stated that this was an example of an exponential decay. Last part, hit the plus sign and add your trend line. So there is the trend line. So if we compare these two graphs that we actually have here, you can see one is actually growing, which was number 28. That one was growing, where number 29, this one is actually decaying. Questions, comments, concerns? Any questions? All right. If not, I would like for you to do number 33 and apply the same principle for number 33. And I'm going to give you a few minutes to work 33, and then I will go through the answer with you, and hopefully you get what I got. So number 33. So hopefully you have this function that I have, 2000 times 2000 times 1.05 raised to the t power. This here is a growth. This is an exponential growth function that we have here. So real quickly, I will show you the Excel, what you should have actually ended up in Excel. Again, we have 2000 times 1.05 raised to the t power. That's the function that we're going to be dealing with. So here is my time exponential model. And this here is going to be equal to 2000 times, open parenthesis, 1.05 raised to the first one, which is 0. This gives you 2000. Scroll it down. So we see here that these are the values. This is going to be my table that you actually have. And then the graph of this. So insert, go to our scattered, and this is what your graph is. This is the graph that we will be utilizing. And then hit the plus sign for your trend line to help connect the dots. Any questions? Any questions? If there are no questions, this is how we will actually deal with our exponential growth as well as decay. Now, there is one other type of problem that we need to consider to make sure that we know what we're dealing with as far as our homework is concerned, and that's talking about half-lives. So if we look at number 45 in your textbook, number 45, we have the following: radioactive waste. A toxic radioactive substance with a density of 3 milligrams per square centimeters is detected in the ventilation duct of a nuclear processing building that was used 55 years ago. If the half-life of the substance is 20 years, what was the density of the substance when it was deposited 55 years ago? So with this, ladies and gentlemen, of course, we will not be dealing with our exponential function, but we will have to kind of modify it to represent half-life. So the function that we will actually be having, or will address this, is Q is equal to Q naught times 1/2 raised to the T over capital T half. Here's that capital T half again, going back to one of the previous sections, I believe in chapter 8, I believe, dealing with capital T W, capital T half. Now, let's look at what the word problem has given us. They tell us that half-life, capital T half, is actually equal to 20. And you can actually identify that if the half-life of the substance is 20 years. So we know what that capital T half is. Q naught, the initial value of this radioactive substance, was 3 milligrams. So Q naught is equal to 3. Now, the last part is this. We need to find out what the value of T is. Now, with T is 55. However, look at the time of T. T was 55 years ago. So because it was in the past, T has to to be negative. So this will be a negative 55 because it happened in the past. So we will be able to find out what the value of Q is. So we have Q is equal to 3 times 1/2 raised to the negative 55 divided by 20. And I need for you to put this into your calculator and round this guy to the first decimal. What do you come out with? Yes, very good. 20.2. Any questions? Questions? Right? If not, well, we're dealing with our last problem for this section, and that is going to be number 47. We're going to be looking at number 47. It talks about in 2000, the median home price in New York City was about 300,000, and from 2000 to 2006, home prices in New York City rose at an average rate of about 11% per year. If prices had continued to rise at that rate, what would the median home price be or have been in 2017? Compare to the actual median price of about 400,000 in 2017. So again, this, we're going back to what we just have, the formula we've just been dealing with is our exponential either growth or decay. And because this thing is growing, ladies and gentlemen, therefore this becomes plus. If it is decaying, we will subtract it from R. So again, this is our growth function. Now, we should know that the starting point in 2000, they tell us, was 300,000. So we understand that Q naught has a value of 300,000. They also tell us that R, it was raised, it was increasing at the rate of 11%, average 11%. So therefore, R is equal to 0.11. So we can kind of go ahead on and say Q is equal to 300,000 times 1 plus 0.11 raised to the T, or just simply 300,000 times 1.11 raised to the T power. This here is the value of Q. Now, what the question that we have at hand, we are looking for what happens 17 years later. So in 2017, what will be the value of the housing market? So we're saying T is equal to 17. So we have Q is equal to 300,000 times 1.11 raised to the 17th power. Please put this in your calculator and round to the nearest whole number. What do we end up with? right? Agree. Basically, 1,768, 5, 2. You can say 7, 8 if you're gonna have that one place behind the decimal. But notice this here is about 1.7 million. That's about 1.7 million. But what was the actual rate? The actual rate in 2017, they said was 400,000. So this is much higher than the actual rate. Now, what could have happened to cause the rate to be so low? Number of things. Housing market. It could have been well, I can't say the pandemic, it was before the pandemic, but several things, job market. So several things could have actually caused it to remain very low. But if it would have continued its trend, it would have ended up being about 1.7 million. All right. Are there any questions? Any questions, comments, or concerns?